ECE 309 oral presentation. Our group is Joshua Metters, Jaime Lopez, and Devin Amirian. Our project that we're doing is submarine depth control, and this project was prepared by Professor Karouche. The automatic depth control of a submarine is obviously very important. The following block diagram represents the system that we're going to be using. The actual depth of the submarine is going to be denoted by C of T. The depth, C of T, is measured by a pressure transducer here, and is compared with the desired depth, R of T, which would be the input. The difference between C of T and R of T is fed back into the stern plane actuator, which will appropriately adjust the stern plane actuator to the proper angle, which is referred to as theta of T. So what we're going to be looking at right now is we're going to find the transfer function h of s, which is our output C of s over our input R of s. The transfer function will be in terms of the gain k of the stern plane actuator. For the second, what we're going to look at is we're going to say that the captain wants to make a dive of 200 feet, which is simulated by R of T is equal to negative 200 U. We're then going to plug in these following values for K and see how that affects the system. K is here. So just really quick, how we're going to find h of s. We're going to take all of this here and combine those and call that g of s. Then this down here we will call h of s. Since this is a negative feedback system, we are using the formula here with the plus. H of s in our model is 1, so that goes away. So our final model is labeled with this equation. And after we model it using MATLAB, this is the final function, and I'll show you now how we get that with MATLAB. What we have here is a pre-written M file. This here is how we find our transfer function. This represents the G, and from the equation that we found earlier, our transfer function is equal to G divided by 1 plus G. We're using the simplify command in MATLAB just in order to make it more legible, more usable function. This, you can see here, our K values represent what we saw earlier, 0.45, 2, and 10. What we have here for P is the P represents the denominator of the transfer function. We want to find the poles of the transfer function, and in order to do that, we take the denominator and find the zeros or the roots of that equation. So this is the denominator of the transfer function. These are the coefficients when k is equal to 0.45. Then we find the roots. We do the same thing when k is equal to 2. These are the coefficients of the denominator. We find the roots, and the same thing for when k is equal to 10. I'm going to run the system, or run this M file, so you can see the output here of what's going on. Here is our transfer function. You can see right here is where the simplification kicks in. Here's our 0.45 for K, our roots, our coefficients for the denominator, and these are the roots here. K is equal to 2. Again, these are the roots for when k is equal to 2. And the same thing for when k is equal to 10. Here are the roots. But now we have Devin, who is going to explain how to use Simulink and how we use MATLAB in order to come up with our block diagram. So here's Devin.
Hi Hi, my name is Devin, and I'm going to be following up Josh's submarine depth control video with how to create this block diagram in Simulink. First things first, we open up MATLAB and click on the Simulink button, which opens the Simulink library. We create a new model, which will open up a blank workspace. If we take a look at the components of the block diagram, we see we have an input, an adder, and a gain for the first three components. The input is a minus 200 step function. So going back to MATLAB Simulink, we could go to sources in the Simulink library, find the step function block, and just drag it into the blank workspace. Double clicking on the block, we could change its final value to be a negative 200. Next, we need to find the adder. The adder is going to be in the math operations section of the Simulink library. Once we found it, we could just drag it, and we need to change it to a negative feedback loop by just changing it from a plus plus to a plus minus. We could then connect these 2 points together. In the block diagram, we have 2 gains. So we could go and find the gain, which is also in the math operations section, drag it into the workspace, drag another one, and rotate it using Control R. We could connect the adder to the gain. Like so. Next, we see we have a transfer function followed by an integrator. So going back to the MATLAB library, or the Simulink library, we could go to the continuous section, add the transfer function, and follow it by the integrator. For the transfer function, we see it's s squared plus 2s plus 1 over s squared plus 0.1. So we go click on the transfer function and only add the coefficients of those values, like so. If we hit apply, we can see our transfer function change into the one matching exactly like the one given. We could proceed by connecting the gain to the transfer function and the transfer function to the integrator. Next, we need an output, a mux, and a scope. The output could be found in the ports and the subsystems folder with just a simple out command, out box. We could just drag it, connect it to the output. Next, we need to add a mux. The mux is going to be in the signal routing section. We could just add that here. Now the mux is used to analyze the input and the output on the same graph. To do so, we need a scope. The scope is under the sinks file. We could just grab it, connect the scope, connect one of the muxes to the output and the other port of the mux to the input. Just do that again. Like so. We also need to connect the gain of 1 into the loop and connect it to the negative side of the adder. Next, we need another scope in order to analyze the angle of the submarine. And we just add a scope, connect it down. Now we could run this system, and if we double click on it, this graph would pop up. If we just auto scale it, this is our result. This represents our input, and this represents our output, which is what the submarine is doing. And next, Jaime will explain all the different values of gain and the analysis for each.
name is Simon Lopez, and now that Josh and David have explained our project and our system, I want to be explaining the analysis on the data. So let's suppose we want to send a signal to the submarine to submerge to 200 feet. We could do this by sending or using a unit step signal with an amplitude of 200. And we're going to be creating different simulations by changing the values for K. So our first simulation here in figure 2.1, it's with the K being equal to 0.45. Now there's a black line here. It's a trace representing the input signal to the submarine controller, and this blue line here, it's representing the depth of the submarine. Now the deepest it goes, it's 350 feet, which is an overshoot of about 75% of our desired steady state, which is 200. And we can see how the graph it never stabilizes at 200, so it just keeps oscillating and it just keeps going and going. Now this is because after we find the poles of the system, we're gonna see why is that. So to find the poles of our system, we can find the roots in the denominator of our transfer function, and those values are these values right here. After we calculated them and previously shown how to do those steps, these are the values that we have now, and we can see that by looking at these poles, they lie on the border of the positive x-plane, and this making the system marginally stable. And this, you can see it here on the graph, how the system never stabilizes at 200 feet. Now our next simulation was ran at when K was equal to 2, and again the black trace is just is representing the input signal of the submarine, and the blue trace is representing the depth of the submarine. Now we can see how the submarine reaches the deepest it goes. It's at 275 feet again, which is an overshoot of 35.5%. So half of what it's way better than our previous K value, but it's still taking some time to stabilize. In this case, it took about 8 seconds to stabilize. Now to find the poles again, we can also do it by finding the roots of the denominator for the system, and then we find those values here. These are the values that we found, and by looking at these poles, we see how the system it's completely stable now after those 8 seconds. Here, so the submarine actually reaches the desired depth that we wanted. Now for the following simulation, we had a K being equal to 10, and we ran it for 10 seconds also, but this time the stabilization came faster now. It occurred like at about 3 seconds, and the deepest it went, it was 225 meters down here, which is 12.5%, and that was a much better case now for the K value. Now to calculate the poles, we can also find the roots of the denominator, and these are the values that we can see right here now. And by looking at those poles, we see how the system it's completely stable now. And by comparing all the previous cases for the different K values, we see how this is the best case we have so far. And after studying and comparing this system with the different gain values, we can see how we can see the importance of the poles of the system. It's pretty much one of the significant conclusions for this project. And every system has a different purpose, and therefore choosing 1K for value might not be the best choice for every different system. And also choosing your gain value is also a factor of cost. So the higher the gain value, the more money that you have to spend on it. So essentially it's a trade-off between the cost and the stability. And pretty much concludes our presentation for the 309 project. And thank you for listening.